Hello, everyone, and welcome to another virtual jug session. And joining us today, our good friend Venkat Subramaniam. Venkat, welcome back to the the V Jug. How are you, Venkat?
Thank you. Pleasure being here. Thanks for having me.
Oh, it's always our pleasure. Always our pleasure. And Venkat, you're home.
Yes,
You're home for a change.
really good to be home finally.
I remember once we had a problem with your. Was it? Yeah, it was. I'm sure it was you, Venkat. There was an internet connection problem, right? When you were in a hotel, I think you set up the internet. It was a 24-hour internet connection, right? And you set it up. Unfortunately, about 23 and a half hours before we started the VJug, right? And halfway through it cut. But you're home, so I'm sure there's going to be no problems like that today, right?
So.
Awesome. And hello to Oleg. Oleg, how are you?
Hey people, I'm doing great.
What's happening, Oleg? I hear there's the mutterings of an amazing report coming out next week.
Yes, it's been taken for a while. We got the survey in the early summer, and then we crunched the results, and we created a beautiful PDF. And now next week it's all ready to go out. So there are some interesting facts in there, some cool statistics. So I hope everyone will enjoy reading that.
Awesome. And so yeah, looking forward to that. I haven't actually introduced Venkat. I probably should introduce Venkat, shouldn't I? Dr. Venkat. What do we have? We have Java Champion. We have Java 1 Rockstar. Amazing author of 9-10 books.
I'm just excited to be home.
Something around that order. Obviously, yeah, massive traveler with trainings and conferences. One of the humblest and nicest people you'll meet and talk to, and founder of Agile Developer. Is it agiledeveloper.com?
Yep.
agiledeveloper.com. So do check out agiledeveloper.com. Venkat also does a whole bunch of other online tutorials and trainings. So do absolutely check that out. I'd very much recommend that. So let me quickly share my screen because I want to go through a few things. Share screen before we get started. Let's go to this one, share. There we go. You can see my screen, hopefully. So we're going to be talking about the power and perils of parallel streams, which is extremely important, really, because a lot of people, when they hear about streams in Java 8, will want to just use them straight away. Oh wow, you can actually add a dot parallel, and they'll do it because they think they can rather than because they should. So Venkat's going to tell us about all the amazing parts of parallel streams and also when you shouldn't use them. As I mentioned, Venkat Subramaniam is an amazing guy. Do make sure you follow him on Venkat if you don't. Venkat _S to follow Venkat. The Virtual Jug is sponsored by Zero Turnaround and Rebel Labs. I started on the wrong slide. Look at that. How silly. Zero Turnaround create revolutionary developer tools for developers, XRebel and JRebel. XRebel has actually just been renamed to XRebel Local, as there is a new kid in town, XRebel Hub. And this is an APM for development and test, so it allows you to run performance testing against your code and monitor your performance against your code during your test environment, and therefore monitor regressions between builds, between dates, and it will give you that information which you can then diagnose and fix using XRebel Local. So there's some really interesting new developments in performance management over on zeroturnaround.com. So do check that out. For those of you who are watching this live rather than a recorded version, you can join us on IRC #virtualjug, and that's on the free node. If you're watching via virtualjug.com, you'll actually see that widget next to the video that's playing. So you can just you can log in and ask questions and also have discussion. Venkat has given me permission to interrupt as and when, so I can pass questions which are relevant at the time directly to Venkat. Please do share the group and session and always provide any feedback you have to me or the Virtual Jug. We also have VJug 24 coming up, a 24-hour conference, which Venkat is actually going to be kicking off and keynoting. So do check that out. It's on meetup.com/virtual jug, and that's obviously free to attend as well. I can't finish this without saying happy birthday to Java 9. 21st of September 2017 is the birth date of our new release of Java 9. So a big congratulations to everyone at Oracle, on the JDK core team, Mark Reinhold, Brian Getz, as well as the community for providing a lot of feedback. I know there's been a lot of people on the virtual jug who have provided feedback at our hack days as well. So thank you all very much. And without further ado, then I'll pass over to Venkat.
All right. Hey, thanks very much again. I'm really excited to be talking about some really interesting things we can do with Java, especially in the area of streams and concurrency. So I want to first of all, I think you mentioned it really well. We look at streams and we look at parallel and we get excited and say, oh my goodness, we could actually use parallel streams. But when do we really use it? What are some of the consequences? That's what I want to really dive into in this hour. So programming concurrency is really hard. It's really easy to start the thread and then the fun begins. It becomes really hard to deal with race conditions to make sure we get good performance out of it. But there are two varieties of problems, I want to kind of set the stage for it, that we normally look at when it comes to using concurrency. And parallel streams only work for just one of them. And one variety of problem is what I would call as a divide and conquer strategy, where you take a problem and then you divide it into two pieces. And then you take each of the pieces and you decide whether you want to just solve it sequentially, that part, or further divide it. And we keep dividing it until it makes no sense to divide further. Well, that's not the problem that parallel streams actually aims to provide. The parallel streams really fit in when we have a collection of data. It could be collection of stock data, could be collection of various other data about people, for example. Currently, I'm working on projects where we deal with several millions of pieces of data that we have to crunch. And so these are really things that fit into really well with parallel streams. Other languages call them as parallel arrays, but with streams, we can readily use these streams for running in parallel. So where does this parallel stream fit in? It really fits into a problem where we have a collection of data and we want to process them in parallel. But let's talk about some of the ways in which we can first create parallel streams, and then we will talk about some of the consequences of this and how we can play with it. Best time to ask questions are along the way, so please don't hesitate to ask questions. Anytime is a great time for questions or comments. Would be delighted to hear what you have to say. So let's get started with a little example here. So let's say we'll keep it fairly simple to begin with. Let's start with a list of numbers, let's say 1 to 6. And I want to just simply transform these numbers. So I'll say numbers.stream. And in this case, we'll just call a map method and we'll call a sample and call it transform. And then in this case, of course, once we transform it, all I'm going to do is for each and just swallow that. I'm just not going to really do anything with the data for now. So what does the transform method really do? Let's start with a transform method, which is not going to do really much at all. So it's going to take a number as an argument. And all it's going to do is simply return, let's say, a number times 1, which is kind of pretty trivial. But what I'm going to do, though, is output. And here we will output the number given to us. And then we will go ahead and output right after that, let's say, the thread information. So we can say thread.current thread, and then print the details about the thread itself. So it's a fairly simple example. We're just looping through and getting the data. And as you would expect, all of them are running sequentially right here. And we also see that they're all running in the main thread. But on the other hand, we can do one of two things to get a parallel stream. We could simply use the word .parallel right here. And then, of course, parallel streams would run in parallel. And we can already see that these are running in other threads. We do see that main is participating in this as well. Well, the beauty of this is the things run in a fork join common pool. And the common pool usually has one less than the number of cores on the machine as the size of the pool. So on my machine, it says that I have 8 cores. My common pool usually has 7 threads. The main being outside of that also participates in it. That makes a total of 8. So you can see that the code as it runs, main is doing some work, and these other worker threads, 1, 2, 3, and 4 are doing some work as well. That's one way to create a parallel stream. But on the other hand, imagine a stream is already there and it's given to you. You don't have the luxury maybe of creating a stream, but to simply use a stream. Well, in that case, you can simply come here and say parallel, and then you can turn that into a parallel stream as well. Now, while we are at it, let's be very careful about this. You may wonder if there is a way I can call parallel, isn't then there's a way to call sequential maybe. And sure enough, you can just convert it to a sequential stream also. Well, that begs the question, if I can make it parallel and make it sequential, hey, maybe then there's segments I can run in parallel and segments when I can run in sequence. And that's when we become, kind of excited about the API and it confuses us and we do it wrong. So to understand this, let's make it parallel one more time. You can clearly see that the map is running in parallel. But if I come down here and say dot sequential, naively I may think that this part is running in parallel, but that's going to run in sequential. But it turns out that's really not the case. So the last call actually wins. So if along the pipeline, until you hit the terminal operation, whatever you said last becomes the mode of operation. So if the last call was parallel, that entire stream is parallel. If the last call was sequential, then the entire stream becomes sequential. So it's really tainting the entire pipeline, not segments of the pipeline. That's something we have to be very careful about when it comes to choosing some of these solutions as well. But having said that, we just took a look at those threads that are there available also, and we can see clearly here that it's running in a common pool thread sharing with main. But what is the order of execution though? That is one thing we have to get really comfortable when it comes to using parallel streams. There is no guarantee on the ordering of how these will execute. Once we set it off to parallel, it's going to bounce off and run in whatever sequence it wants to. So if you look at the numbers being displayed right here, you can see 4612 as the value. And if we run this again, we can't really predict what is going to be the sequence. It could run in any order. Now, with the same token then, if we come here and call a print over here, so let's go ahead and say sample, let's say : print, and we're going to print out the result. So we'll just copy this for now as a print command. And in this case, of course, this is going to be a void method. We'll just call it print. And within the print, all I'm going to do is again print the number and the current thread within the print itself. So we'll just go ahead and say p:, and then we'll just go ahead and print it right there. So in this example, when we run this though, notice that as it gets printed, it's printing in different order. Let's go ahead and comment this out so it's a little easier for us to see the output of the print itself. And you can see the sequence varies quite a bit. It printed 4, 5, 6, and 2. But if I run this again, it could be a completely different sequence. Who knows what the sequence would be, 4, 3, 2, and 5, for example, and so on. So the good news is all these executions are running in parallel. The bad news is there's no guarantee on sequence. But unfortunately, if you're producing a report, you can tell your users, I've got a good news for you. The report is really fast, but too bad, things are jumbled up. That's not going to really win our business. So how do we really control the order? Well, make no mistake, it still runs in parallel, but you can say for each ordered right here. And when you say ordered, it says that that terminal operation, I'm going to perform in an ordering. So until the previous one in the order finishes, I won't run my part. This only makes sense when the collection itself is ordered, and then it's going to guarantee that ordering. So when you notice in this case, when you run this, you can see that it is running in that order. But however, it is running in parallel at the same time, though. It just is running in sequence at that point. So notice the map ran 1, but the map ran also things like 4, 5, and 2. But the 2, even though got finished, couldn't run until 1 was finished. But 5 got finished really before 2 did. But 5 is not running until 4 got finished. So we're imposing the ordering in the very end of this. And that's how we could actually use ordering. And there are certain operations that do ordering implicitly, as we will see later on. And also you can do ordering explicitly by using some methods which have the word order in it. In this example, we just saw that the map is running parallel. Likewise, filter can run in parallel as well. So if you just throw in a filter right there, it's going to run. When you're running filter and map, what is unique about filter and map is I call them the swim lane operations. I call them swim lane operations because when you perform a filter and a map, It only works on the current element. It doesn't look for the elements on the left. It doesn't look for the elements on the right. Its focus is entirely on the current element. The filter decides whether to let a particular value go through or not. It doesn't care about its neighbors. Similarly, map transforms a value. It doesn't care about neighbors. On the other hand, reduce does things very differently. Let's go back here and understand how reduce is going to work. So for this, let's go ahead and create a very little method here called add. And let's say this add is going to take a total, which is a partial sum, and then the value. And all it's going to do is simply return a result of this computation. Well, the result of this computation is going to be result is equal to, we'll go ahead and say total plus the value. Now, given these two, we want to apply, let's say, an interesting reduce operation on this. So we'll go ahead and say dot reduce. And the reduce is going to start with the initial value of 0, let's say. And then in this case, let's say we're going to simply say sample and call the add method on it. This is going to, of course, give us an eventual result of adding those values, totaling the values 1 through 6 in this particular example, giving us a value of 21. But the sequence in which it runs, though, is, if you notice, it's going to say, let's go ahead and print out right here the value for total. So we'll say total is going to be the value total, plus let's go ahead and say the value given to us, and then we'll just print out the value itself. We'll say value, and we'll just print those two values along the way. So as we can see in this little example, we have the total initial value 0 coming in, the value 1 from the current element. The result 1 is carried over as a total in the next call. The result of 1 plus 2, which is 3, is carried over as total in the next call. That's how reduce actually works. So this makes sense, but what does reduce really do? Reduce essentially takes the initial value 0 and works on the first element, takes the result of that, carries over to the second element, takes the result of that, and carries over to the third element. So it may make sense that this actually is sequential, but as it turns out, this can actually run concurrently as well. So to understand this, let's go ahead and print out here a thread dot current thread. And then, of course, in this case, when we run this, you can see that it's still sequential, all of them running in the main thread. However, before we understand how parallel is going to work, let's reason what this actually may actually mean. So let's say for a minute, you are trying to total the age of everyone in a room. But it's quite possible that the people in the room, maybe there are 100 people in the room, you could be walking through each one of them sequentially and totaling all their age values. But instead, let's say these people are sitting in different tables, let's say 6 person per table, and then you have the second table with these people and maybe a third table and so on. Well, there's no reason why we have to do them all sequentially. We could start totaling or reducing people on one table. While we are doing that, we could reduce the ages for people on the second table and the third table and so on, and we could do it concurrently. And then once we do it, we could then take those sub-results and then merge them together. Maybe we'll take the sub-results of one side of the room, and while we are totaling it, we can take the other side of the room and total the subtotal, and finally take the two subtotals and merge them together, kind of like a tree structure. So work on each table in parallel, work on the sides of the room in parallel, and then merge them together. If we're going to do something like that along the way, it turns out that reduce can actually run in parallel, and in fact, it does. So if you go back and run this little example, what's going to happen in this case is, of course, if I spell it properly, so parallel, and in this case, of course, when I run this, notice that the reduce is actually running in parallel. You have these workers that are running it, but notice also the total values given in the beginning. All the total values are 0 in the beginning because as it starts working on each of the segments, it uses that initial value 0. And then, of course, you can see that later on, it is using the results from the previous computation into the next one. This brings up a very important thing to keep in mind. What is this value 0? Let's go back here and comment this out for just a second. Let's also comment this out for a second. Run the code. The result is 21. But what is a 0? Well, the 0 is not actually an initial value. The 0 is actually an identity value. So what does that really mean? If you're going to total, 0 is a good value to start totaling. But if you're computing a product, then the value would be 1. So if your goal was to total all the values, but then total, let's say, a 10, when you run this sequentially, notice the result is a 31 instead of a value of 21. But this is a really bad way of programming with the reduce, that is. And the reason is, if I were really interested in doing this, a right solution would be to come out of this and add a 10, because notice the result is 31. But if I put that 10 over here in the beginning and run it sequentially, the result is still 31. However, the minute I turn this into parallel, the result is no longer a 31. Gosh, it became an 81. What's the point in getting a result really, really fast, but a wrong result? So we need to really understand what just went wrong. 10 is not a good identity for this operation. So we have to be very careful. And if you really stare into this a little bit, you will notice that the 10 value really was passed in for a number of these as initial values for these little segments. That's not going to be fun at all doing. So what do we do about this? Well, a better solution would have been to use the identity of 0 still, but then in the very end, what we really want to do is to come out and add the 10 eventually, and you can see the result is still 31, which is what we want to use. So keep in mind that these have really good consequences. These are identity values, and reduce does run in parallel, but we have to be very careful how we run that as well. Probably a good time to see if there are any questions before I move forward. Any questions at all from anyone, actually?
We have one question. It's quite a general question. Happy to give it to you now if you would like.
Sure, please.
It's from TCH on IRC asking, should we use parallel streams at all? Stack Overflow will tell you it's inefficient in the default case.
Well, it really depends on the problem. I don't really try to generalize things quite often, because any generalization is bound to, probably that including that statement itself is going to be wrong. So I would use the context. I'm actually using parallel stream on my project right now. I can't tell you how much we actually get performance out of it. We cannot imagine. So it really depends on what we are trying to do. If you can cautiously use it and get results out of it, absolutely.
Awesome. I think that's everything we've got. Thank you.
Yep. All right. So let's talk a little bit about, using parallel stream. How many threads are we going to have, and why is that thread count so important? Well, let's first of all ask the question, where are these things running? We already saw that right here. Notice all of them are running in the common pool thread. So let's quickly examine the common pool thread just to kind of get a sense of what's going on here. So let's go ahead and say over here, output, and we'll say fork join pool, and then we'll say dot common pool, and then we'll get access to the common pool from the fork join pool of concurrent package. So what does that really tell us? Well, it is telling us that the concurrency level of this, I'm going to run this on the command prompt so it's a little easier for us to see the output. So you can see that in this case, it says parallelism is 7. Well, that's because on my machine, I've got 8 cores. And so the common pool has 7 threads. And remember, main is part of it as well. So that totals up to 8 different threads. So, but why is there 8 threads? Why did they choose to have as many threads in the pool as the number of cores on the machine? Well, the reason for that is by default, it's the number of cores. But imagine you're running a computationally intensive operation. If you're running a computationally intensive operation, you should not give more threads than the number of cores. And the reason is your cores are going to be busy running your computations. If you have more of these tasks waiting, they're going to ask the threads running to context switch to other tasks. So when I have enough work to do, I'm going to stop what I'm doing and then pick up the next task when I could be working on what I already have, on my hand. So as a result, as you increase the number of threads beyond the number of cores, you might actually get, poorer performance. I've actually created examples where if you run this code in parallel with more number of threads, you can actually perform way poorly than even the sequential code. For example, in one example, our sequential code took 5 minutes to run. By increasing the number of threads in parallel, we resulted in this taking about 30, 40 minutes to run and still not get the results back to us. So we could really do poorly by increasing the number of threads. On the other hand, if I'm using I/O problems, or where I'm going to be sleeping on I/O, maybe my code is talking to a database, opening a file, requesting data from a remote service, what have you. In those cases, I could actually have more threads dedicated to this job, where that may make sense, than the number of cores. But how many though? Well, we could actually come up with a really easy formula to do this. So let's talk about a little formula here. Let's say we have what is called a blocking factor. So blocking factor is going to be a value 0 less than or equal to the blocking factor less than 1. This is the percentage or a rate of time your thread or task is going to sleep without doing active work. If I am computation intensive, then I am going to, what is it going to do? That's going to be a blocking factor of 0. If I am I/O intensive, it is going to be, about 0, but maybe it's a 0.5 if I'm blocking half the amount of time, maybe 0.9 if I'm blocking most of the time, hopefully not 1, that would be a deadlock. But then we could say the number of threads that I can have in my program is actually equal to, and this formula is actually pretty easy to really come up with, and we can say the number of cores. So we can say number of cores, and of course this is going to be number of threads, and you want the number of threads to be less than or equal to the number of cores divided by, and we can say 1 minus the blocking factor. So what this says is, let's run through this math real quickly. If I'm computation intensive, my blocking factor is 0, so the denominator is 1 minus 0, which is 1. So the number of cores divided by 1, you don't want the number of threads to be any more than the number of cores. If my blocking factor is 0.5, that means I'm sleeping half the time. When I'm sleeping, you might as well use the CPU, the core, for some other task. So we could have 2 tasks running on a CPU. When one is sleeping, the other could run. So you could have twice the number of tasks or twice the number of threads. So 1 minus 0.5 is 0.5. Number of cores divided by 0.5, 2 times the number of cores. If it's 0.9, on the other hand, you could have as much as 10 times the number of cores as the number of threads. But of course, the question is, how do you determine the blocking factor? Well, you have to use tools and techniques to figure that out, but that gives you a formula as to how many threads you can have. But what if I give more threads than what I should really give? In that case, I would actually see poorer performance. And for the safety reason, the default thread is chosen to be equal to the number of threads, number of cores on the machine. So that brings up the question, if I want to vary the number of threads, how do I actually do this? So to understand this again, let's go to a fairly simple example here to consider this. Let's go ahead and say we have the transform method one more time. And in this case, the transform, all I'm going to do is just print the thread details. I don't want to really print anything more. So I'll go ahead and say return the number again, but this time we'll output a thread.current thread so we can actually see the thread details. But in this case, I'm going to have maybe about 20 different values that I want to really use. So thread.current thread, and let's go ahead and say numbers over here, and numbers.stream, and we will go ahead and call the map method on this, and say sample transform. And once again, the for each is going to just simply, not do anything with the result provided to it for now. So if I run this little code here, we are going to receive the data, and we're going to, of course, this is going to be the value E. I'm slipping at the wheel. There we go. And we can see the threads are still in the main thread. But let's go back here and increase this to maybe a 7, 8, 9, and all the way up to, let's go ahead and say, a bunch of values, maybe 20 different values. Well, it so turns out my machine has only about 8 cores, or at least that's what this program says. Well, but if I have 8 cores, how is this going to get scheduled if I'm doing it in parallel by default? So if I go ahead and say dot parallel right here and run this, we're going to see these running in bursts. Well, 8 cores, so the first 8 get scheduled right away. And as they start finishing, the next 8 are going to get scheduled, and then the remaining are going to go on. So in this case, it's going to run in 3 batches. Let's see if that's actually true. So let's go ahead and run this over here. Burst 1, well, in this case, of course, we're going to put a delay so we can actually see this. So let's go ahead and say sleep of, let's say, 1 second, so we can actually observe this really easily. And let's go ahead and write the sleep function here. And as a result, if I go back and run this code now, you can see that in this case, it's burst 1, burst 2, burst 3, and done. So you can see that it actually ran in 3 bursts right there. So that shows us that it's scheduling on those 8 different threads, which are part of the common pool, and scheduling in those 3 batches. But what if I really want to increase the number of threads? Maybe I know that this is really I/O intensive rather than being computation intensive. I want to give more threads. There's one option, and I would say this very reluctantly, not a great idea, but at the JVM level, you could say the Java util concurrent fork join pool common parallelism equals whatever value. I really love this property. Finally, some property which is more, longer than my name. This is really nice. Well, I'm going to use this property as a -d option, and because I'm lazy, I wrote a little script to set this in a command line, and I'm going to run that as run config right here. This is going to ask me for the number of threads I want to provide. If I say 100, you can see that it does that in 1 burst, boom, and it's done. And as you can see, it just took 1 burst to do it. On the other hand, if I said 2, well, I have 20 values that's going to run in 10 bursts, and you can see that it's scheduling on those different bursts. Now, why is this such a bad idea to use? Well, the reason this is not a really smart thing to do is it gives a very easy way for us to customize the number of threads, but this is going to be universal across the JVM, which means if I have a mixture of computation-intensive tasks and also I/O-intensive tasks, then all of them are going to run on that pool size because we just simply increase the common pool size. We're not going to get good performance out of this if for computation-intensive jobs, so we could run into problems. So this really depends on what you're trying to do. If your application is extremely narrow or very specific, maybe you can use this, but maybe not otherwise. But you can programmatically configure this as well. And the way to programmatically configure this is to create your own fork join pool. Let's take a look at an example of how we can actually do that. So here is a piece of code that's running in parallel. Let's just grab that and replace this with just a call to run for now. And then within here, let's go ahead and write the method. We'll call it as public static void run. And we'll just put the code inside of that run method. So all I did was just move it around just a little bit. Obviously, in this case, if I just run this, it's going to run in 3 bursts, as you can see, 1, 2, and 3. And that's what it just did. But notice also more important, these are running in the common pool right now. On the other hand, let's do something a little silly here. We'll say if math.random is greater than 0.5, I'm going to say output, we'll say running, let's say from main. And in this case, I'll just call the run right here. Otherwise, we'll say output running, let's say from a pool. And I'm going to create a pool and run it from that particular pool. And I haven't done the job yet, but you can see that it's running in the main, but half the time it's going to just go ahead and run it in the other half. And that's what we want to really implement, running from the pool. So what do I want to do for the running from the pool? I'm going to say over here, well, I already have the concurrent given here. So we'll say fork join pool, and we'll create our own pool right here is equal to new fork join pool. And in this case, let's go ahead and set up maybe 12 threads in my pool. So that's going to run in 2 iterations, burst then 3, or we can just go ahead and say 50 for now. So it'll just run in 1 burst. And I'm going to say pool dot shutdown. I'm just used to shutting things down as soon as I create them, so I don't forget it. But I'm also going to say pool dot await termination. And in this case, we'll give it, let's say, about 10 seconds. So we'll say time unit over here. And let's say, in this case, dot seconds to give it some time to wind down. This is going to require handling exception, but I'm not interested in doing that right now. So I'll just simply say throws exception as an easy way to get around it. Well, what are we going to do within here? All I'm going to do is simply say over here, pool, so pool dot, And in this case, we will simply say submit, and we'll provide a little lambda, and we'll call the run right within this. Alternately, you could also call this as, if you're into using method references, simply say sample : run. That's fine as well, whichever you're comfortable with. But the point really is, now the run method is being called within a pool. So when it comes in here, this execution is going to run begin to run within the other pool. And because it's running within another pool and not in main, so if you start the execution in main, then it uses the common pool. If you start the execution in another pool, it's going to use that pool. So this gives you a fine-grained control over how you want to do things. Let's go ahead and run this real quick again. Notice it's running in the main, so common pool again. But if I run this one more time, hopefully it flips over with the randomness, and then we can see that it's going to run in the other pool. Well, that's when the demo doesn't do what you really want it to do. I'll try this one more time. Otherwise, I'll switch over to just running that in the other pool. So let's go ahead and just comment that out and force it to run in this other pool. So in this case, of course, I'm going to ask it to run in that other pool we are creating and do the submit on it. Let's go ahead and run that now and see, and you can see that it runs in the fork-join pool worker. So the point really is, it really depends on where you are running this from. The main, then it goes to the common pool. On the other hand, if you were to run this from within another pool, it's going to make use of that particular pool. I want to talk about some perils of using some of these things. But before I do that, I want to yield to see if there are any questions along the way.
So yeah, we have one question coming in here from Buland in IRC. We do not limit parallel threads to the number of cores, as for example in the case of a web server, though that web server running on a few core machines still supports many parallel thread or file descriptors, and we need that because if it's bound to the number of cores, then it's difficult to expand. So is there any reason you add a limit on that?
Well, because it's a question is IO intensive versus computation intensive, right? So if you are on a web server, what do web servers typically do? They are not as much number crunching as they are doing mostly, IOs. Your requests are extremely short-lived in those cases. When we talk about computation-intensive jobs, you've got number crunching going on for a very, very long time, and the CPUs are kept busy crunching these numbers. Talk about systems that do weather forecasting, for example. You're not going to run your weather forecaster on a web server, right? These are going to be dedicated servers that are going to run these number crunching. A web server is on the very far end of that spectrum. Most of what we do is, IO. You're reading a database, you are reading files, you are producing certain, content very quickly, and then you're pushing it off to your request. In heavy enterprise systems, if your request is going to perform enormous amount of computations, they would very rarely want to do that on web servers. What you would do then is you would take a request from the user and then put it off onto other systems on the back end, which will do the number crunching for you and get the response back. So that's one of the reasons why typically web servers have a lot of threads compared to number of cores, because they have to open these connections and serve these connections extensively. They are very far away from number crunchers. On projects I'm working on, we do heavy duty number crunching. We take millions and millions of data and we run them through math models. We got to be very careful. But this is exactly why we have tools like Spark. Now, imagine I have a very heavy computation, big data, number crunching project on a given machine. If I have 128 cores on this machine or 256 cores on the machine, I have run to the limit of the number of threads I can have for the number crunching. So this is why you have things like Spark that says, I'm going to make distribution of these concurrent code across a cluster of machines easy for you. Why do we want to cluster across machines to do these? Because we will not get better performance on a single machine because we have reached the limits because of number crunching. And tools like Spark say, Well, don't sweat about it. I'll make it very easy for you to distribute this problem using the RDDs or the distributed data sets, and I can distribute this across machines, run the computation on these machines, and bring the results back to you. So we have to be very careful understanding the nature of the problem we are dealing with when it comes to parallelizing. If we parallelize a problem without understanding the nature of the task and the computations, we then end up getting really poor performance, and that's not going to be fun to work with. So it's really a good question to ask, why do web servers do that? Because the nature of things they do is very different from computation-intensive jobs.
Awesome. And one other question from Dwarak. Can we not use parallel and yet run in a pool? So can we run in a pool and use normal parallel?
I apologize. I don't think I understood the question. When you're running it in parallel pools, you can still run it sequential, but if you're going to run it in your own pool, it's going to use that pool. So I'm not quite following the question. I apologize.
So I think the question is, he says, can we not use parallel and yet run in a pool? So maybe can we run in a pool without using parallel?
Yes, you can. And when you do, okay, I think I understand the question. If you are in a pool, and let's say you take a collection. Okay, let's actually go to this example. I think this illustrates really well. So in this example, as you can see, if I run this now, I want you to quickly notice the worker threads are different thread values, right? 30, 23, 26, and so on. So it is using the pool right now. But if I go back and say, don't do parallel, well, it is running in a pool for sure. That's no doubt about it. But if you look at the output in here, that's going to be sequentially running on just one thread in the pool. So we are in a pool, but we are sequential within the pool. We're not quite making use of the pool. This is as good as running in the main, if you will, for all practical purposes, if you want to think about it that way. So the point really, in this case, it actually timed out at that point, 10 seconds. But anyways, the point is, it is sequential. So in other words, when you have a lot of data on your hands, you want to run it parallel or sequential is an orthogonal decision you make. The pool where you reside is just an implementation detail. It's kind of like a road on which you want to drive your car. You decide what car to drive, but the road is going to be the implementation. So whether you run your code in a main or whether you are a common pool or whether you run in your own pool is orthogonal to whether you run it sequential or parallel within that context of the pool itself. So typically, if you want to make use of the pool, you would want to schedule the pool, but also run this in parallel as well. I think we can take one more question before I go to the next topic, if there is one.
Okay, so there was only one other question that I actually answered, but it's worth mentioning it on the video as well. It's the obligatory which IDE you're using there.
Oh, I'm using TextMate, but if people are interested, if they go to agilelearner.com and they can type in the word TextMate, they will find it. And so the URL for that is, I'll just mention it right here. It is http, and then www.agilelearner.com. So, and then you just type in the word TextMate in the search box, and then you will find it. That's TextMate, M-A-T-E.
Thank you very much.
Sure. And let's go ahead a little further and talk about, what are some of the perils of doing this? Well, parallel does not always mean fast. And there are times when we could run the code in parallel and we may get a much slower result out of this. So we have to be very careful in doing this. So if I have a very highly computation-intensive task, by increasing the number of threads, we might actually get a very poor performance overall in our code. So let's see if we can actually do this right here real quick. If I have these values given to me, and I'm going to just keep it as very simple, let's just grab these values for a minute. And in this case, let's say for each of these, I'm going to perform a computation. So get rid of all of these things and simply drop this in here. So in this case, if we have these 20 values in this collection, I'm going to say a stream dot, let's say a run, numbers dot stream, and let's go do a map operation right here. So in this case, I'm going to say a dot map, and let's go ahead and call the sample and call the transform method. And then we'll go back and say reduce, and we will ask it to reduce to a single different value. So we'll go ahead and say total comma value, and then we'll just return maybe total plus value in the very end. So given this, you can see that the transform method is going to work on every single value in this particular collection. Well, but what if I were to do some very high number crunching operation in here? So what if I were to say for, let's say, well, let's start with a value, let's say int, result is equal to 0. And I'm going to say for, let's say, int I equal to 1, I less than number times, let's say, a max. I don't know what that value is right now, but we'll come back to that. And then we will go ahead and say result, let's say, plus equal to math.square root of that particular, let's say, value I right now. And then eventually I'm going to return the result back to the caller of this particular method. Well, I don't care about the real actual computation itself right now. And then, of course, in this case, we'll say 0.0 just to make the compiler a little bit happy. Well, if this is going to be a large value, let's say a static final, and so what is the good value for max? Let's say the max value is going to be, a large value. Let's say 100,000 as the value to begin with. So this is going to loop through the values, and I'm going to keep increasing this a little bit later. And then, of course, it's going to do that for, let's say, all these values given in this collection, and it's going to do all these computations. But obviously, I'm going to do this in parallel to make this really fast. So I could say parallel right here. And in this case, of course, we're going to run these in different threads. But I got a lot of these jobs that are going to be very intensive in running. And how much time is it going to run to produce the result? If I just try to run this sequentially, assuming I don't have any compilation errors on it, I do. So let's fix line number 22. So line 22 is not too happy. Well, that's going to be, let's see where it's ending. So that's ending right there. I don't think I need to deal with exceptions right now. We'll remove that. And numbers.stream parallel. I'm not seeing the error right now, but we'll figure it out. So where's the line 22 is illegal start of expression. That's what it says on 22. Let's look at the main function. So in the main function, of course, I'm going to say numbers.stream. And oh, of course, this is Java. Don't put a comma in the end. All right. So when I run this, it's still having some trouble with the types over here. So this is going to be total plus E. Where's the value coming from? Let's try, how about this? Let's say map to double and do a sum so we can reduce some of this code right here. Maybe we can see that it's running a little faster with that. So, so what is the result value? Double, of course. Let's go ahead and say double. All right. Hopefully I've cleared that all. Well, that's going to take some time to execute after all and produce the result of all those computations. Let's go ahead and output the result right now. But in this case, of course, we are running this sequentially and trying to get the result of these operations in the very end. Let's go ahead and run this and how far it takes. That's running. It was not too time consuming. We'll say time and then run it. And how much time it's going to take to run this sequentially. I'm going to bump it up enough to get a little bit slowness on it. That was still a 0.82 seconds. Let's make this about maybe 1 million objects, iterations through to run this. And that's taking a little longer to run. But if I want to parallelize it, how much performance am I going to get out of it? Well, it took about 2 seconds to run. What if we turn on parallel on this one? And remember, I have the number of cores equal to number of threads by the default execution that I'm going to do right here. So a sequential run a minute ago gave us what it did, about 2 seconds. And here we got about 1 second. So not too bad, right? We're running it a little parallel. We're getting a better performance, whether we can squeeze more out of it. But what if I do time and run configure, and I'm going to provide it 1,000 threads. Now, 1,000 threads, notice that in this case, we could argue maybe I was a little slow in typing this, but the point really is, even if we try to give a lot of threads to this, we are not going to get better performance out of this code, and mainly because it is going to spin all these threads and do context switching. By giving more threads, we are not going to get a better performance out of these things. In fact, I'll try to do this again. So we'll say cat 1,000, and then we will go ahead and say time and then .run config and see if that's actually going to work. And oh, that doesn't work. So let me try the other way around. So actually, let me edit the file. So I'm just going to hard code it so it doesn't ask me for the input. So in this case, I'm going to make a copy of this. So run config, I will call it copy it. So run config copy.sh. So that way we can really see the amount of time we're going to spend on this. So get rid of most of these things. I'll hard code the value for the number of threads. So right there is threads, and let's make that about 1,000. So what are we going to get out of this particular code when we run this? So time again, and we'll say run config. And what does it tell us? Well, that's taking about 1.3 seconds. It did not do any better than the other code did. And we can keep bumping this even more, and I can increase the problem size, and it's going to get really, really worse. That's one thing to consider. The second thing is there are certain problems where running them in a particular order is very important. So we need to be very careful in parallelizing it. A third problem to consider is when we start making these things parallel, to give you an example of this, one day I went to work, and a colleague of mine said, the program runs fine sequentially. When I ran it parallel, it ran really fast, but the result is a disaster. And the immediate answer from me was, oh, you have a mutable variable someplace, and that's messing up. And now it was trying to search for a needle in a haystack. And we had to go through the code to find where that mutability was. Good news, we found that in 20 minutes. And then we refactored the code to remove that mutability. And now we got really good performance and thankfully the correct result as well. So mutability and parallel doesn't go together. But there's one other thing we have to be very careful about, two things. When should I not maybe use parallel? Well, one of the things to keep in mind is when it comes to a job that is really small, maybe you have a very small collection, or you have a task that is really, really fast, then it may not make sense to make it parallel. Let's take an example. Let's say you're home and you have two, fairly grown-up children, and you say, hey, I'm running out of sugar. Go over to the neighbor and get the sugar. One of your children jumps the fence. The other one goes out the door to maybe get into a car or a bicycle or a scooter or a motorbike, whatever. Well, which one is going to get the sugar really fast? The one that jumps the fence, because the neighbor is right next door. It's quicker to just jump the fence and go on, especially if it's a really friendly neighbor. But on the other hand, if you want to go to the store about 5 kilometers away and get something, the kid that jumps fence is probably going to go to the jail. So you really want them to use the right tool based on the size of the problem, the complexity of the problem. So smaller collections, quick tasks may end up wasting performance due to context switching. On the other hand, if you have a long-running task or computation intensive or IO intensive, you might benefit from having more threads. But there's one other thing we have to be very careful about when it comes to parallel. It really comes down to understanding what we are buying into. So to understand this, let me switch over to a slightly different problem here and illustrate the point of that right in here. So what I'm going to do here is to get a collection of people objects. So notice I have a collection of people on my hand. But what I want to do is the following. I want to write a little piece of code that says, find the first person older than, let's say, 25 years of age. So I'm going to output right here. And I'm going to start by saying people. So people, and people is going to come from a collection. So let's say person, and we will say people is equal to create people. And in this case, I'm going to start out by saying people.stream. And then I will ask it to do a filter, and given a person.getAge is greater than 25. But then I say map, given the person, get me the name of the person. Let's say that's what I really want. And then I'll say find first. And then finally, I'll say or else, maybe I'll say, no one, no name. Well, given this example, when I run this sequentially, it says Paula. But I'm curious, what did we really perform? Remember, streams are lazy. So if I go to the person class in the getAge method, if I output getAge for, and then the plus the name, notice that when I run this, it's going to examine Sarah and Sarah, Bob and Paula, but it would never touch Paul, Jack, and Jill. So when I run this though, notice it stopped with Paula, didn't go any further. Let's go back and comment this out for a minute. What's going to happen if I were to run this in parallel? So dot parallel, and I'm going to run this in parallel. Let's run this on the command line a few times. So I'm going to say run right here. And in this case, I want to run it maybe about 6 or 7 times at least. So if I were to run this many times, you will notice the result is going to be absolutely consistent. It's always going to be Paula each time you call this. And that's because find first is much like your for each ordered. So it is going to make sure that it's going to get the result for you in that order because you said, I want the first one. Make no mistake, these are running in parallel. If you're curious to know that they're running in parallel, you can put a little thread and you can see it. However, this stream is fundamentally lazy. So what does lazy mean? Lazy means I won't do any work that is unnecessary. I'll be efficient in avoiding work that shouldn't be done in the first place. When you run this in parallel, on the other hand, you are not following that model. Parallel is intended not for reducing work. Parallel is to get faster results. So here's an example. Let's say I have a room of 100 people. I was walking around and helping them. Let's say I've left my cell phone next to the third person in the room. Now, when I want the cell phone, I don't know where I put it. Quietly, I can walk to the first person, check if they have it. No. Second person, no. Third person, yes. I took 3 units of time, 3 units of effort, and I got my cell phone. Alternatively, I could just yell out in the room of 100 people and say, folks, could you please check if I have my cell phone next to you? Well, the third person still finds it. How much time it took? 1 unit. How much effort it took? I disturbed everyone in the room. So the good news, I got the result faster. The bad news, I disturbed everyone in the room. The good news, I don't care. Well, the point really is, my goal was to get the result faster. If I don't want to disturb as many people, do as much work, then parallel is probably not the answer at that point. So in other words, when it comes to parallel, we are interested in throwing much more hardware and work on it to get the result faster. So notice in this example now, when I run the sequential many times, I am getting the result, but it's always Paula, but I never touch anyone after Paula in this example. On the other hand, though, when I run it in parallel, well, good news, I'm still getting Paula as the answer. Of course, you may argue, cannot run it 15 times and prove it, but trust me on this one. However, if I were to show what threads are running, it's a very different world, as you can see in this case. What's going to happen is I'm going to run this in parallel, of course. So let's make sure I save it. So that's parallel. So in this case, of course, when I run it in parallel, it is going to do a lot of extra work. Notice it did touch Jill, it did touch Jack, and all the other objects came through as well. So when it comes to running these things in parallel, you might actually do more work. And if these work are going to continue for a while, you might be holding them resources. You sure got the result really fast, but there are still computations running in the background that could be a disadvantage. So we have to make these very critical decisions. Similarly, if you're using a find any instead of find first, it's possible that you may get any result, not just the first one, and you should be okay with it. It may not be the same consistent result every single time. So to summarize what we talked about, the parallel is very powerful to solve one category of problems for us, and that is problems that can be taken into a parallel array, and we can take collections of data and work on them in parallel. I definitely want to emphasize, I have greatly benefited from parallel. We are actively using it on our projects where we are crunching huge amount of data. We cannot live without it. But also at the same time, we have to clearly understand it's very easy to turn on parallel, but the consequences can be really bad if we don't understand what we are doing. So it's our responsibility to be sure we are doing these things for the right reason, and we could be doing it incorrectly. The traps are still there. We have to be very careful how we actually end up using this.
Okay, awesome. We have a couple of questions on our seat. One from Nathan. Does Parallel Streams use thread affinity internally?
Use what?
Thread affinity.
I don't think they actually do, but I've not really looked into it.
Okay, yeah. I mean, just to add to that, I think without having state on the threads, I don't think there's any point in having an affinity anyway. So yeah.
And by definition, fork join pool should really give you the flexibility to switch over. So I don't think it does, but I could be wrong.
Okay, question from Dodi. How does Java 9 stream when work with Parallel? Oh, how does Java 9 stream when work with Parallel? Does it stop all from getting run?
I don't think I know.
Yeah, Dodi, if you could add a little bit more to that question, that would be awesome.
Yeah.
We also have a question from Oleg. Oleg, do you want to ask that question?
Yeah, so like you showed a bunch of API to us. Would you recommend using the built-in Java Streams API framework in the JDK, or do you think it's reasonable to look at different implementations, RxJava or StreamX or something that maybe has a larger?
I think certainly we should look at different implementations, but we also have to understand the problems they solve as well. In our project, for example, we use parallel streams, but we also switch over to using Spark where it makes sense. So we kind of go back and forth depending on what we are trying to do. And also, the problem of concurrency is quite different from the problem of asynchrony as well. So with RxJava or various other tools, it's not quite, they are not doing exactly what the parallel streams do. So the use case for them is different. I would actually argue there are good cases for them to be mixed together as well, where it may make sense.
Okay, I believe I understand that question now. It's not when was actually I'm trying to find the names of the methods. When was actually tried to be a method name. I think it's drop while and take while are the actual two method names that Dodi is talking about. So how would they work? How would drop while and take while work in a parallel stream?
Yeah, so think about it much like you were find first, if you will, right? So find first. Really, the efficiency of find first hinges on the laziness, and so does drop while and take while. So when you start processing these things, remember these don't have any side effect. They shouldn't have any side effects. So when you use them in parallel, it is quite possible you did some extra work behind the scenes. And one thing I've noticed, this is exactly the case as limit, because limit is already there in Java 8. Limit is just a different case compared to take while and drop while. Take while and drop while are special cases of limit. So when you use limit with parallel, what you would notice in your code is you actually generate a lot more data than the ones you actually end up using for exactly the same reason. Laziness is one thing. Parallel is a completely different thing. Laziness says, I will do only the minimum work needed. Parallel says, bring it on. I'm going to do as much as I possibly can, get spinning, so I can get the results really fast. So to answer that question, the behavior of drop while and take while will be exactly like the behavior of limit that you do in Java 8.
Okay, awesome. There are no other questions in IRC, so it leaves me just to say a massive thank you to Venkat Subramaniam. Yeah, is it Agile Learner or Agile Developer?
Well, Agile Developer is my company, and Agile Learner is my video site. Got
it. So yeah, do check out agilelearner.com. And go and see. There are plenty more videos. Actually, I quite like the videos as well because they're like little mini videos. So if you're quite interested in a specific topic, Venkat will give you a really good overview of like this mini topic. So do check out agilelearner.com as well. Then, Venkat, thank you very much, and we'll see you again on VJUG 24 on October 25th.
Right. Well, thank you to both of you and everyone who's listening. Thank you.
Absolutely. Thanks, everyone, and see you next week, everyone. We have microservice communication, what, where, when, and that's going to be a session on September 26th, on next Tuesday. And after that, at Java 1, I believe Roberto Cortez is going to be running a book club, Integration Testing from the Trenches, with Nicholas Frankel. So yeah, do go to them, and then it's VJUG 24 after that. So to everyone else, have a great evening, afternoon, morning, wherever you are. And thank you very much to Venkat. Thank you very much, Oleg, and see you all next time.
Thank
Bye
you.
for now.
Bye.